Alright everyone, this is the last section of chapter 5. This is section 5.8. In this section our goal here is to be able to use intercepts to graph polynomial functions. So some concepts of polynomial functions, we have that a 0 is a number k, and it's a 0 of a polynomial function f. It's where that crosses the x-axis, and if you plug that value into the polynomial you will get back 0. A factor is x minus k, and it will be a factor of the polynomial f of x that is factored all the way down completely. A solution is just a number k that satisfies the polynomial equation, the polynomial f of x equals 0. So if you plug that solution value into the polynomial, you will get back 0. An x-intercept is a real number k, and k is an x-intercept of the graph of the polynomial function f if that value crosses the x-axis at that point k0. So for example 1 here, what we're going to do is use x-intercepts to graph a polynomial function here. Okay, so what I want to do first is figure out my x-intercepts. Okay, so my x-intercepts here are going to be coming from the stuff inside the parentheses there. And we want to flip the sign on because they're factors and we want to flip the sign on there. So x is going to equal -3 and x is going to equal 2. So if we put these as a point form, that's -3, 0, and 2, 0. So we can go ahead and graph those on the graph. So -3, 0, and 2, 0. There's where they're going to cross the x-axis. And now we're going to kind of like talk about our and behavior a little bit that we talked about in section 2. So our degree here, we have at most 3 factors here because our x minus 2 is repeated twice. That means we have at most 3 solutions. Okay, so that'd be -3 and then 2 is repeated twice. Okay, so since we have 3 solutions, there's really a degree of 3, and our leading coefficient is that 1/6 here, and that's positive. Okay, and we talked about end behavior in section 2, and we said if a degree is 3 or odd, and our leading coefficient is positive, then it's that regular snake-looking kind of curve, and it's going up from left to right. Okay, so we know it's going to look like that sort of shape here in a minute. But in order to figure out other points on that S-shaped curve, we need to make a table. Okay, and if we were to plot that whole, or plug in that whole polynomial into the graphing calculator underneath y equals and pull up the table using the blue second button and then graph in order to pull up the table, those buttons. Okay, we want to use maybe x values -2, -1, 0, 1, and 3. Okay, we could also use -4 if we want to go beyond -3 or that x-intercept there. But if I plug in -2, the table tells me I got back 8/3. And then -1 is 3, 0, 2, 1 is 2/3, and 3 I got back 1. Okay, so 8/3, if I want to kind of graph -2 8/3, 8/3 is about 2.67. Okay, so at -2, 2.67, about right in here. And then -1, 3, 0, 2, 1, and 2/3, which is about 0.6 repeating. And then 2, 0, that was our x-intercept, and 3, 1. Okay, and even if we were to throw in -4, it would keep going down forever. And if we kind of make our smooth curve here, it is in fact the smooth shaped S regular snake kind of a curve that we got from our degree in leading coefficient. Okay, so how we can talk about how many turning points there is going to be in our graph is another important characteristic of polynomial graphs. Okay, these turning points correspond to local maximum and minimum values. So thus far we've only talked about maximum and minimum values back in chapter 4, okay? But these are going to be more than one maximum or minimum. So, for example here, a local maximum occurs at the y-coordinate of a turning point of the function if the point is higher than all the nearby points. So our local maximum, according to our graph here, at negative 1, 3, that's a local maximum, 3 being the highest y-coordinate than the x-coordinates, or than the y-coordinates around it, nearby. And the local minimum occurs at the y-coordinate of a turning point of the function if the point is lower than all the nearby points. So our local minimum over here in our graph is 1, negative 1. Negative 1 being the lowest point than the nearby points around it. Okay, so we're looking for local maximum and minimums to help graph polynomial functions here. So the graph of every polynomial function of degree n has at most n minus 1 turning points. And if a polynomial function has n distinct real zeros, okay, so n distinct real zeros, then its graph has exactly n minus 1 turning points. Okay, so with these, we want to make sure that we have the graphing calculator ready. We're going to graph this function, we're going to identify the x-intercepts and the points where the local max and local mins occur. Okay, so the first thing I probably want to do is think about my degree of the polynomial, or the highest exponent. That is 3 right now. And our leading coefficient, or LC, is 1, so that's positive. So we know it's going to look like a regular snake-looking kind of graph. Okay, now I want to go to my graphing calculator and plot and plug in x to the third minus 3x squared plus 6 underneath the y equals button. Okay, and what we're going to do is once we have that, we're going to hit graph. So the graph button. And once we have that, we're going to want to find zeros and the local max and local min. But if you hit the second button, the blue button there, and then hit trace, which is the second from the right white button up top, and we could pick whatever we want. We could pick 0 if we want to find a x-intercept there. We can hit the minimum or the maximum. But say I want to hit the minimum value. Okay, so we have that graph already pulled up, and I want to find the minimum, or the 0, one of the zeros. Okay, what I'm going to do is hit second and trace and hit the 0 function, and it's going to ask for a left bound. So you're going to hit something to the left of where you think the 0 might be, and then you want the right bound too. So after hitting enter for the left bound, you're going to hit enter after you tab over to the right from the right bound. Okay, then it's going to ask to guess, and you're going to hit enter. And when you hit enter, the x-intercept it's going to have is approximately 0, 6. Or 2, 2. No. Wrong one. Negative 1.2, 0, 0. Okay, so at negative 1.2, 0, that's our x-intercept right now. Then we could do the same thing to find the local max and local min. If you hit the second trace button again and hit minimum, and then do the left bound, hit enter, and then tab to the right for the right bound or upper bound, okay, and hit enter. It'll ask to guess, and you hit enter again, and it's going to give you the minimum, or the local minimum. Okay, so that local minimum, it tells you is going to be at 2, 2. Okay, and then finally, if we go second trace again and hit the maximum for the local maximum, and then it'll ask you either the lower bound or left bound, you hit enter, then you tab to the right on the graph to where you think the local max is, to the right of it, hit enter, and then hit guess, or when it says guess, hit enter, and it will say that the local max approximately is at 0, 6. Okay, and according to our end behavior, we can kind of draw that S-shaped kind of graph. So it kind of goes up, and then goes back down again, and then goes back up again. And that really did not work. Here we go. Okay, so it looks like that S-shaped kind of curve that we thought it was going to be according to our end behavior there. Last one we're going to look at is this last example here. We're going to do the same thing, talk about our degree. Our degree here is 4, and our leading coefficient is 1. So since my degree is even, that's the U-shaped kind of graph, so we know it's going to look like a U. And again, if we go through that process of putting in that whole polynomial into y equals, and then hitting the graph button, and then we try to figure out what the zeros or the x-intercepts are. We hit second button and then trace, the white button, and if we hit the 0, and we go through and try to figure out the points exactly for where they cross the x-axis, those zeros there, or x-intercepts, there's going to be 4 in this case, okay? Because that makes sense, because there's 4 x-intercepts or solutions, which is the exact amount of the degree that we have right now. So if we go and repeat that process, the x-intercepts are going to be approximately negative 1.140, 0.290, 1.820, and 5.030. So if we kind of graph those, negative 1.14, 0.29, 1.82, and 5.03. Okay, there's where they're crossing the x-axis. Then if we go and search for our local minimums, we're going to do the same thing. Hit the second blue button and hit trace, go down the minimum, and repeat the lower or left and right bounds, okay, to try to figure out the local minimums. And one will be negative 0.57, negative 6.51, and the other one's going to be 3.96, and negative 43.04. Okay, so if I do my local minimums at negative almost a half and down 6.5 pretty much. Here's this one, and then 3.96, which is close to 4, and then down 43 will definitely be off the graph, but I'll just put it down here. Okay, and what we have left is the local max. So if we go hit the second blue button again and trace, and we go to maximum, and we do the left and right or upper and lower bound for that one, where we think it's going to be at the local max for that is approximately 1.11 and 5.11. So we can graph that 1.11 and 5.11. So right in here somewhere. And now all we need to do is, according to our end behaviors, kind of sketch that kind of a graph. Okay, so when, oops, I kind of graphed that in the wrong place. Positive 1.11. There we go. Alright, so now what we need to do is just draw our smooth kind of curve. So it makes the first local minimum. Here's our local maximum. Here's our second local maximum, or local minimum, excuse me. And then back up. So it is kind of that U-shaped kind of curve, and it has 3 turning points, which makes sense because it has n minus 1 turning points at most, okay? And it has 4 distinct real zeros. That was what we graphed there. So it has exactly n minus 1 turning points. Our n, in this case, was our degree of 4, and n minus 1, or 4 minus 1, is 3, so there's 3 turning points, and exactly 3 turning points there.